Okay, so right triangles and the right triangle ratios that we've talked about in the first video of this chapter can be used to model lots of different phenomena that occur in the real world. And so we're going to explore a couple of these different types of problems. Just remember, this is used all over the place in engineering, construction, architecture, all kinds of stuff. So it's very useful to know. All right, so in example 3, we're talking about wind speed and how it affects the angle at which a kite flies. This table that you see shows the angle the kite line makes with a line that's parallel to the ground for several different wind speeds. You're flying a kite that's 4 feet above the ground and using 500 feet of line. We want to know what altitude is the kite flying if the wind speed is 35 miles per hour. Alright, so since we know that the wind speed is 35 miles per hour, we know that the angle of the kite line makes a 48-degree angle. So when you have a problem like this, especially a word problem that's talking about a real-world situation, I always like to start off by drawing a picture. First off, we know that the kite that's being flown is 4 feet off the ground. Okay, so we have a person, they're holding their kite. Obviously, I'm not an artist, but they're holding the kite 4 feet off the ground. Okay? Now, that's where they're holding the base of the line. The kite itself has 500 feet of line, and we have our kite right here. Okay, and it's up in the air. We want to know what's the altitude of the kite if the wind speed's 35 miles per hour. So the altitude is how high the kite is above the ground. Okay, so again, we have a rough picture. Now, you might see it, but what I've done, if I draw that line parallel to the ground, is I now have made a right triangle. And that means this little portion is 4 feet. So what I can do is I can use my right triangle ratios to find this piece right here, and then just add 4 feet onto that to find the altitude at which the kite is flying. We know that since the wind is 35 miles per hour, we know that this angle right here, our theta, is 48 degrees. So now I've got everything I need. Obviously, based on where the right angle is, this is our hypotenuse. Based on where the angle is, this is our opposite. So very similar now to the videos that we've already seen. What trig ratio uses opposite and hypotenuse? That's sine. So I'm going to use sine to solve this. So sine of theta is the opposite of their hypotenuse, and I'm going to plug in what I know. I know the angle was 48, so sine 48 degrees is equal to the opposite, which I don't know, all over the hypotenuse, which was 500. I want to get the opposite by itself, so what I'm going to do now is multiply by 500 on each side. Multiply by 500 on each side. And over here on the right, the 500s are actually going to cancel out. So I'm left with 500 times the sine of 48 is equal to the opposite. And I'm just going to use my calculator. Again, my angle was given in degrees, so be sure you're in degree mode like we discussed in the previous video. If you're not in degree mode when you need to be, it's not going to come out correct. So I have 500 sine of 48, enter. So the opposite is approximately 371.57 feet. If I round to 2 decimal places. Now again, that's only this portion, this side of the triangle. But I know that I initially held the kite 4 feet off the ground, so I need to add 4 to this to get the total altitude of the kite, which is what the question was asking me to do. So my final answer is going to be about 375.57 feet above the ground. So the kite is, you always want to make complete sentences. So the kite is about 375.57 feet above the ground. That's my answer. Okay, again, We used right triangle trig to find part of the altitude, but we had to use that information we were given at the very beginning. We're holding the kite 4 feet above the ground to begin with. Okay? So another problem. We have another word problem, no big deal, so we're going to start off by probably drawing a picture, so we need to be paying attention for keywords that's going to help us to draw that picture and fill it in. So we have an airplane that's flying at an altitude of 30,000 feet, and it's headed toward an airport. To guide the airplane to a safe landing, the airport's landing system sends radar signals from the runway to the airplane at a 10-degree angle of elevation. How far is the airplane measured across the ground from the runway? All right, so let's first start by drawing the ground. The airplane is flying at an altitude of 30,000 feet. So altitude is always up and down, so that's 30,000. And so up here is our airplane. Okay, mine kind of looks like a shark, but you know, whatever, get over it. I'm not an artist. Okay, but my airplane is flying toward the airport, the landing strip. Okay, and it's descending at a 10-degree angle elevation. All right, we want to know how far along the ground that we have. So this is what we're trying to find. How far away from the airport? How far away from the airport is the plane across the ground? Okay, so now that we have our picture, and it's not a very good picture because again, I'm not an artist. How far away is this? So we want to start by filling in our picture with the information related to right triangles. First off, let's figure out the hypotenuse is always across from our 90-degree marker. Based on the angle that they gave us, 30,000 is going to be on the opposite side of the triangle. And then the part we're trying to find is the adjacent part of the triangle. Okay, so now what we need to ask ourselves is what trig ratio, sine, cosine, tangent, cosecant, cotangent, or secant, which one of those 6 ratios will use both adjacent and opposite? Well, the one that pops in my head is tangent. So tangent of theta is the opposite over adjacent. I want to plug in what I know. I know the angle is 10 degrees. The opposite is 30,000. And the adjacent, I'm just going to call that x because that's the piece I'm trying to find. Okay, well, I want to get that x by itself. So to do that, I've got to get rid of this fraction. So I'm going to multiply by x on both sides. X is just a number, so we can multiply it. It's just we don't know what that number is. So don't be scared about multiplying by a variable. That's totally fine. All right, so the x's cancel out on the right-hand side, and so we're left with x times the tangent of 10 equals 30,000. Now, we want to get x by itself, so what I'm going to do now is divide by tangent of 10 degrees on both sides. Again, tangent of 10 degrees is just a nasty decimal. You could round here. However, I suggest you wait and round at the very end. The tangents are going to cancel out, so my answer that I found, x equals 30,000 divided by tangent of 10 degrees. And let's figure out what decimal that is using our calculators. So 30,000 divided by tangent of 10 degrees is about 170,138.45. And this was in feet away from the airport. So the plane is about 170,138.45 feet away from the airport across the ground. And that's what we were asked to find, so this is our answer. Okay, so the airplane's still pretty far away, but it needs a lot of room to descend safely and land safely so it doesn't crash up and hurt anybody. Okay? Again, right triangles can be used to model lots of different real-world situations, so just be sure, always start off by drawing a picture, label your picture with what you know, and from there it's not too hard. Okay? Just a little bit of algebra. Let me know if you got questions.